Now we're going to actually define a new term called the definite integral. Now this is really nothing different than what we were doing on the previous pages. The definite integral from x equals a to x equals b is really your accumulated change from x equals a to x equals b. So suppose we have a rate function. We're going to call the rate function g of x. G of x is really to be thought of as a rate function, a derivative f prime of x. So we're going to call it g of x, but you want to think of this as the derivative of f of x. It is a rate function. Suppose our rate function is a continuous function from a to b. Then the definite integral of our rate function, the definite integral of g of x on the interval x equals a to x equals b, is denoted with this notation. See your integrand symbol here. When I write integral a to b g of x dx, integral of g of x from x equals a to x equals b, that is the definite integral of g of x from x equals a to x equals b, and we want to understand what we're calculating when we find this value. So first of all, one way to think about it, the integral of g of x from x equals a to x equals b gives us the amount that f of x has increased or decreased from x equals a to x equals b. It is the accumulated change of f of x on that interval. Okay, so this may look very complicated to you at first, but let's come down here and look at an example. So one thing I may ask is how much does f of x equals x squared increase or decrease on the interval from x equals 4 to x equals 7? So we have a function f of x equals x squared, and we want to know how much it goes up or down from x equals 4 to 7. So to figure that out, we could plug in x is 4 to the function. We get 4 comma 16. So it goes through 4 comma 16. And we plug in 7, the 0.749. So again, this is a y equals x squared function. We're saying you can go from x equals 4 to x equals 7. And when I ask how much does it increase or decrease, well, we plugged it into the function, we found the y values, and we determined that it increases 33 units. Because it went from a height of 16 to a height of 49. So we were able to use the function f of x to make that determination. So this integral, this definite integral, gives us a different way to go about finding that same answer. So the idea with the definite integral is I don't have the function f of x. Instead, I'm starting with the derivative of f of x. The derivative of f of x, right? F of x, remember, was x squared. Its derivative is 2x. So we're saying we're starting with the rate function g of x is 2x. Remember though, g of x is just f prime of x. We're starting with f prime of x is 2x. We're going to take this rate function and we're asking how much did that original function f of x increase or decrease on the interval from x equals 4 to x equals 7. Well, the way that we write the notation for that question is to write the definite integral of g of x from x equals 4 to x equals 7. Notice that we have this dx here on the right side. You want to think of, when you're writing these definite integrals, that this integrand with the 4 to 7 is on the left, and you're going to think of it like parentheses in a way. You open up this definite integral notation over here on the left side with the integral from 4 to 7 symbol, and you close it on the right side with this dx. It's saying we're integrating with respect to x. You have to close it off with the dx at the end. If you had a function f of t, you would probably integrate dt. You're integrating it with respect to the variable t. Okay, so opening with the integrand symbol on this side, closing it with the dx on the right side. So we're integrating from x equals 4 to x equals 7. The function g of x is actually 2x, so I've replaced g of x with 2x. So we're integrating from x equals 4 to x equals 7, 2x. And what this calculation is asking us to do is find the accumulated change in the original function, f of x, from x equals 4 to x equals 7. Now, when you're looking at integral of 2x dx, you don't know the original function it came from. What you know is that 2x is the derivative of the original function. And you're asking yourself, well, if 2x is the derivative of the original function, what was the original function and how much did it go up or down from x equals 4 to x equals 7? Well, in our case, for this particular example, we know 2x is the derivative of x squared. So we can evaluate x squared at 7 and evaluate x squared at 4 and subtract to find the change that's occurred. Now, what we're actually doing here is called the fundamental theorem of calculus. It's the second part of it, and we're going to talk more about this in upcoming videos and how to do this step. Right now, all I want you to get out of this is a big picture understanding of what we're doing when we find a definite integral. When you're finding a definite integral, you are integrating this rate function on that interval, and you're identifying from that how much the original function increased or decreased on that interval. Now, another way that we saw that we can interpret what we're doing here when we find this calculation is an area between the rate function and the x-axis. And again, we count area below the x-axis as negative. So one way we did it is we said, well, we're thinking about how much the function y equals x squared goes up. It goes up 33 units from x equals 4 to x equals 7. This other way that we can interpret what we're doing with this calculation, the integral from 4 to 7 of 2x dx, is to think about the graph of y equals 2x, the actual rate function. G of x equals 2x. But remember, 2x is actually f prime of x. Another way to think of it is f prime of x is 2x. Here's a graph of f prime of x is 2x. Right? It's a linear function. If I just skip over here and say this is 4, x is 4, the y value would be 8. If we jump over here to x is 7, the y value would be 14. And when we ask to integrate the function 2x from x equals 4 to x equals 7, what we're actually doing is we're finding the area between this rate function and the x-axis. It's the area of this figure here. Notice that would be a little triangle up here and a rectangle here. And if you find this area between the rate function and the x-axis from x is 4 up to x is 7, you will find that that area is 33. That area is telling us how much the original function x squared increased on that interval. It's positive, so it's increase. This last one, we're going to come back to that one when we actually do a little bit more work first. We'll come back and talk about that. This is more of the technical definition of that definite integral. The technical definition involves a limit of the areas of rectangles as they get smaller and smaller, and we'll come back and talk about that. So we'll just leave that there. All right, so for now, what I want to do is go back to the examples that we did on the previous pages, example 1, 2, and 3, and we're going to just add in the notation for the calculations we did. We found accumulated change. Now, instead of calling it accumulated change, we're calling it the definite integral. So let's go back to those examples and add the actual notation in for what we were doing. On the first page in example 1, we had been given a rate function, r of t equals 400. And we found the area between the rate function and the x-axis from x equals 0, x is 5. What we were calculating here was the integral from 0 to 5 r of t dt, integrating the rate function from t equals 0 to t equals 5. Now we actually know the equation of the rate function is r of t equals 400. So another way to write this is to say the integral from 0 to 5 of 400 dt. And we actually calculated it. We calculated this value by finding the area between the rate function and the x-axis from 0 to 5. We found that the area was 2,000. So the definite integral value is equal to 2,000. Again, when we interpreted it in terms of the original population function, we said on this original population function, the population increased 2,000 on that interval from t equals 0 to t equals 5. Let's look at example 2 and try again. So in example 2, we were given a rate function. This time our rate function was a constant function. R of t equals negative 2,000. It's a constant function below the x-axis. What we calculated was the integral from 0 to 5 for r of t dt. The definite integral gives us the accumulated change in the original function. The accumulated change was that the profit went down 10,000. We count that area as negative because it's below the x-axis. So the integral of r of t dt on the interval from t equals 0 to 5 is negative 10,000. R of t can be replaced with negative 2,000 because that's the actual equation. R of t equals negative 2,000. So the integral of negative 2,000 from t equals 0 to t equals 5 is negative 10,000. Again, what did that mean? It meant our profit function went down 10,000 units on the interval from t equals 0 to t equals 5. And in example 3, we actually performed 3 different calculations in this one. We have a rate function. R of t equals 5t minus 20. The first thing we did was we found the area of this big rectangle below the x-axis. We found the area from t equals 0 to t equals 4. It was all below the x-axis. So what we calculated there was the definite integral from 0 to 4 r of t dt. Since we know the equation is r of t equals 5t minus 20, we can really write that as the integral from 0 to 4 of 5t minus 20 dt. And we get a value of negative 40. The tank drained 40 gallons during the first 4 minutes. Then we did the calculation where we found the accumulated change from minute 4 to minute 6. That was the area of this little triangle up here. And in terms of the definite integral, what we were doing was finding the integral from 4 to 6, r of t dt. We know the equation of r of t, so we can write this as the definite integral from 4 to 6 of 5t minus 20 dt. When we performed the calculation, we found that the accumulated change was positive 10, that the tank increased 10 gallons during that time period. Then finally, overall, we put these two together. We said, well, the tank first drained 40 gallons, then it gained 10 gallons. Overall, it lost 30 gallons during this entire time span. So you can also do the same with your definite integral. We can put it all together and say the definite integral from 0 to 6 r of t dt is definite integral from 0 to 6 of the function 5t minus 20 dt, and it comes out to negative 30. On that time span, the accumulated change is down 30 gallons. On that time span, the tank decreased 30 gallons overall.